Welcome back. Today we're looking at section 3 of chapter 1, which is about infinite limits. That's limits that go to infinity and limits as x goes to infinity, asymptotes, and piecewise functions. So first we're going to look at infinite limits, and this is where the limit itself goes to infinity. The the graphs look kind of like this. We saw this in section 1, where the limit doesn't exist, and we'd look for the left-hand limit and the right-hand limit. So from an equation, how does this happen? Well, the equation of this graph right here is f of x equals 3x minus 5 over x minus 2. To find the limit, say as the limit as x goes to 2, any other limit on here will just give us whatever that function value is. But the limit as x goes to 2, we're going to plug in 2 just like we've been doing. 3 times 2 minus 5 over 2 minus 2. That gives us 1 over 0. Now yesterday we saw dividing by 0 and we had to do something else. Well, that was when it was 0 divided by 0. When it's a number divided by 0, that's all right. Well, it's kind of all right. We still don't get a limit, but we get one of these guys where it's going to infinity or negative infinity or one of each. And now we just have to figure out which it is. And so to do that, we are going to just look on each side so we can have the one-sided limits. In this case, the limit as x goes to 2 from the negative side, we can plug in numbers that are a bit smaller. The 3 times 2 minus 5 is always going to be 1. It doesn't matter if 2 is just a little bit less, it's still going to be 1. That's going to be positive. So it's going to be 1 over, and then we can look at, as it's going to 2 from the negative side, 2, a little bit less than 2, 1.999 minus 2 is going to be 0, but it's going to be a negative number. I know I always notated 0 negative. It's like a negative 0. It's basically 0, but it's negative as we're approaching that number. So 1 divided by a negative number is going to be negative infinity, which we see from this graph right here anyway. And then going from the positive side, it's the same thing, but we're going to be looking at it from that direction. And so we'd be plugging in numbers just bigger than 2. So as we're looking at the limit as x goes to 2 from the positive, again, the top's going to be 1. That's not going to change. Yeah, it's going to be something very, very close to 1, but for all intents and purposes, it's 1. And then the denominator, we're going to plug in numbers just bigger than 2, 2.000001 minus 2 is going to be that very, very small positive number. So we're going to get a positive 0, and 1 divided by a positive number is going to be positive. 0 still takes it to infinity, but it's positive infinity. And again, we could see that from the graph, but that's just kind of what's going on in the equation. And so while we're here looking at these infinite limits, it seems like a good place to talk about vertical asymptotes, because we can see the vertical asymptote is happening right there as well. And so infinite limits happen at vertical asymptotes. So how can we tell when it's a vertical asymptote? It's when the denominator equals 0. And so we just set the denominator equal to 0. In this, and it would be from the function, not the limit. So in this case, we just need x minus 2 to equal 0. We can add 2, so x equals 2. That's the vertical asymptote. If we have one that's just a little bit bigger, say f of x equals x cubed minus 2x squared plus 3 over x squared plus 3x minus 4, first of all, we don't really need to worry about the top. Now, it actually is a good idea to factor the top and factor the bottom. We're going to have to factor the bottom anyway, because common factors make wholes. They don't make vertical asymptotes. In this case, the top does not factor, so we don't need to worry about that. So we just need to look at the denominator and set that equal to 0. So x squared plus 3x minus 4 equals 0. This will factor. X plus 4 times x minus 1 equals 0, which means that x could equal negative 4 or x could equal positive 1. Those would be the two vertical asymptotes for that problem. So those are the infinite limits, when the limit itself is infinity. Yes, it doesn't exist, but it's basically infinity. So now looking at limits as x approaches infinity, these look different because the limit is as x goes to infinity of f of x. It's not as x goes to a number. It's as x goes to infinity. The nice thing about these is that they do not require any math or calculations or anything to solve and find. We find these based on observation. We can look at the equation and know what it is. First of all, the f of x is generally, in this case, it's going to be a fraction. We're going to have something divided by something else. Generally speaking, a polynomial divided by another polynomial. And so what happens is we have all these rules. Basically, we're looking at the degree of both the top and the bottom. This first case, if the degree of the top is bigger than the degree of the bottom, then it won't have a limit, because it's just going to keep either increasing or decreasing. And so an example of this could be the limit as x goes to infinity of x cubed minus 2x squared plus 7 over 3x squared plus 5x minus 6. Again, all we need to look at are these first terms, because that's where the degree comes from. These other guys don't matter. We could see how it is with, like, mathematically, we'd be multiplying by 1 over x to a power, which would get rid of everything else. But in general, only those first ones, the biggest degree, makes a difference. In this case, the top has a bigger degree because it's cubed. The bottom's only squared. And so this one has no limit. If we look at the second one, if the top degree is smaller than the bottom degree, then the limit as x approaches infinity will equal 0. The example of this, limit as x goes to infinity of x squared plus 2x minus 5 over x cubed minus 6x squared plus x. Again, we only need to be concerned about those ones with the biggest degree. The bottom is bigger than the top, and so the limit equals 0. And then finally, we have the third one, if n equals d. If the two degrees are equal, as in this case, we're only concerned about these guys. 2 degrees are equal, you can pretty much just cancel. I know that's bad math to be able to do that. With infinite limits, that's kind of what ends up happening. Again, there's a few other steps along the way, but that's basically what happens, and you end up with just the ratio of the leading coefficients. So in this case, it would be 2/5. And so those are limits as x approaches infinity. Now you might be thinking that that looks a little bit familiar. You've seen that before. And you would be right. We've seen that actually the past couple years. We just haven't been talking about them as limits. We've been talking about them as horizontal asymptotes. The rules for horizontal asymptotes are the exact same as the rules for infinite limits, or limits as x approaches infinity. The difference is how the answer is written. And the question would give us f of x equals this fraction, but then a horizontal asymptote is a line. It's a horizontal line. So instead of no limit, well, all right, the first one is no horizontal asymptote. That's boring. It has an oblique or slant asymptote, but that's not what we're looking for. The second one, instead of the limit equals 0, y equals 0. Instead of the limit equals 2/5, y equals 2/5. And that's all there is to horizontal asymptotes. It's the same as limits as x approaches infinity. Same thing. How you write your answers slightly different, but the process is identical. Our last topic today is looking at limits of piecewise functions. So if we have piecewise functions, the place that we're going to be figuring out where the limit is in most situations is going to be at the breaks in the domain. It's going to be at -1. It's going to be at 2, because that is where it's actually entertaining. Otherwise, it wouldn't matter if it was a piecewise function. If we were finding the limit when x equaled -5, we would just plug -5 into the top equation because that's the one that would include x equals -5, and the rest of them wouldn't matter. But to find them at the breaks, we're going to have to find both the one-sided limits as well. And so the first break is x equals -1, so if we want to find the limit as x approaches -1 of f of x, we first have to find the two one-sided limits. So from when x approaches -1 from the left or from the negatives, you're looking for when is x less than -1. So you're going to have to plug it into this equation. So we're just going to plug -1 in there. I know that -1, like x can't actually equal -1. That doesn't matter. We're finding the limit. We want to know what would it be if it could get to -1. And so we plug -1 in. -1 squared is 1 minus 3 is -2. So the limit as x approaches -1 from the left is -2. Next, we're going to look to see when it approaches f of x from the right. For that, you want when x is bigger than -1. So we're going to use the middle equation, plug in -1, -1 minus 1 is -2. And then for the limit itself to exist, these two things have to be equal. They are equal, so the limit exists, and it equals -2. For the limit as x goes to 2, again, we need to find both one-sided limits. When x goes to 2 from the negative side, we need the numbers less than 2, which is going to be the middle one. This time the middle one's first, but notice the middle one gets used for both because it's in both domains. So we plug in 2. 2 minus 1 is 1. And then we need, as that goes to 2 from the positive side, so when x is bigger than 2, we're going to plug in 2 to that bottom equation. So we get -2 times 2 plus 6, that would be -4 plus 6, which is 2. To find the overall limit, we look at the two one-sided limits. Those two things are not equal, and so the overall limit does not exist. And so that's generally how you find limits of piecewise functions. Now, in the last section when we were finding limits, we had a lot of fractions, we had a lot of things you had to factor and do a lot of stuff like that. Generally speaking, that doesn't come on inside of a piecewise function. It could, but it doesn't usually. Usually piecewise functions, the limits themselves are actually easier. You just need to know to be able to find each of the one-sided ones and then see if they're equal or not. So that is section 3. Be working on your problems, be asking questions as needed, and we'll try to get them answered. And until then, happy mathing.